Welcome to Lesson 18, Module 5, Sampling Variability and the Effect of Sample Size. Okay, and again, this is something that we have been talking about quite a bit over the last several lessons. It's this idea of variability. Okay, we'll talk more specifically about that and also about the effect that sample size has on your results, or the, let's say, reliability or validity of your results. Okay, this lesson is actually a continuation pretty much of lesson 17. It's going to use that example from lesson 17 about time spent at the gym. We'll refer to that one. It's not going to be, like I said, as has been the case in this topic, topic C, it's not going to be very calculation heavy, but more or less just process heavy and vocabulary heavy. So yeah, with no further ado, let's go ahead and begin. Okay, so here we have example 1, and it's called sampling variability. Okay, so let's go ahead and take a look at this. So the previous lesson investigated the statistical question, what is a typical time spent at the gym? Okay, that was the question that was broached. And again, any kind of statistical study like this, there's always a question. All starts from a question. All great science and math and the rest start from good questions, one good question. Okay? So anyway, we selected random samples from a population of 800 gym members. Remember, we had those charts of 800 specific times. Okay, 2 different dot plots of sample means calculated from the random samples from the population are displayed below. Okay, so 2 different dot plots, and these are ones that not that we had generated, but that they have generated for us. Okay, so 2 different dot plots there. Now the first dot plot, okay, that's that top one, okay, represents the means of 20 samples with each sample having 5 data points, okay, and it's probably worth taking a little time to talk about that and what that exactly means, because that is probably the most confusing part of this entire lesson, and we can celebrate that. Okay, so there are 20 samples, all right? So 20 different sample populations were drawn, okay? But each of those samples, okay, had 5 data points, okay? So there were only 5 different times were pulled from them, okay? Were pulled from the population of 800 different times, okay? So again, this idea of sample, 20 samples, 5 data points. Okay, so let's look at that a little bit more closely. Okay, so again, let's go ahead and look at this 20 samples of 5 data points. So for example, here is our population. These are the 800 different times spent at the gym. Okay, so each sample would have been, just for example, so 1, 2, and I'm just of course making this up, 3, 4, 5, and again, randomly generating these numbers and coming up with these. So that would have been 1 sample, okay? So in this case here, in this top dot plot, okay, there were 20 different sample sets just like this that were 5, okay? So altogether, there were 100 data points that were selected, okay? So 100 data points were selected for that top one. Okay. Now those were the means. So right here, there are still 20 dots. Okay, 20 dots. So what happened is that for every sample size like this, for all of these, okay, if I added up all of these and I found my mean. Okay, so let's say that's 52 minutes, whatever was the mean of that one. Then I would do that again, another 5, 3, 4, 5, okay, whatever, another 5, and then that's another mean, let's say that's 60 this time, and on until I had done that 20 times, okay, all right? but each time, each sample is only 5 data points large. Okay, so 5 data points large. Each sample is includes 5 data points only. Okay, now the difference between that and this one here, there are still 20 dots on this dot plot. Okay, still 20 dots, but now these means, and each dot represents a mean or an average from a sample. Okay, includes here, and you can see it right here, 20 samples, with each sample being 15 data points, having 15 data points. So the difference here now, so instead of taking a sample, 20 different samples of 5 data points, which would mean 100 data points chosen, okay? Now we are taking, each sample 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So that is one sample, one of 20. Again, now I figure the mean, and let's say that's 60, I don't know, 62, whatever, and then I'm going to do that 20 times. So each one sample mean, into it went the average of 15 different data points now. Okay, 15 different data points. So each sample in this dot plot, each sample mean, which is each dot, had a lot more data go into it. In fact, if we looked at that top dot plot, there were 100 data points chosen. In this bottom dot plot there are 300 data points chosen. Okay, so a lot more went into it, and hence the difference in the way it looks. And you can see, again, these are 20 different means, okay, 20 different points or dots that represent 20 different means, okay, from 20 different samples. The only difference is that the top dot plot had less data go into it to come up with its separate means, okay? All right, and again, let me just point out here, when you see this over here, n equals 5, and that means sample size. In statistics, when you see that n equals, that's a lowercase n now, okay? That lowercase n always means that's your sample size, okay? Has nothing to do with the number of dots. It has to do with each sample had either, in here it had 5 for the top dot plot or 15 for that bottom dot plot, okay? Alrighty, so go ahead. Let's go ahead and have you answer these questions here, and then come on back and we can discuss them, all right? So based on the first dot plot, okay, Jill answered the statistical question by indicating the mean time people spent at the gym was between 34 and 78 minutes. And you can see how she did that, because you have 34 is here and then 78 is here. So it's somewhere in between, which makes good sense. That's quite a range though, all right? But she decided that a time approximately in the middle, because she went ahead and, not necessarily arbitrarily, but she said, well, let me just find something that's right in the middle, and she decided that was about 52 minutes, okay? So she chose this one here, right about here. It doesn't have to be a dot there. It doesn't necessarily have to be a dot there. And in fact, there is no dot where she chose her mean to be. And again, this is just, she's guessing. There's like the same number of dots on this side as there are on this side. She's actually choosing a median, in fact, okay? But now the other guy, Scott here, he answered the question using the second dot plot. And he indicated that the mean time people spent in the gym was between 41 and 65 minutes. Okay, so he chose these right here, because this is where most of the action is occurring. Well, actually, all the action is occurring. But you can see now that range has lessened. Okay, it's gone from being, this big up here, okay, this wide range, to a smaller range here, okay. But he also selected 52 minutes to answer this question, all right? So they both chose 52 minutes as their mean, okay, well, again, this is a predicted mean, all right? They haven't actually crunched all the numbers, all right? But they have two different looking dot plots, but they chose that same mean. So I would like you to do this, just ponder this, think about these three questions here, or three statements. So the first one, describe the differences in the two dot plots. Which dot plot do you feel more confident using to answer the question? Okay. And then in general, do you want sampling variability to be large or small? I'm saying, see if you remember what this term here means, sampling variability. Okay, so go ahead and answer those and come on back and we'll discuss them. Okay, so we can start off with this, this first one here, describe the differences in the two dot plots. Well, I mean, some things you could have said, and probably the main point here is it actually shows the first one, the first dot plot shows greater variability, okay? So greater variability in the sample means. Variability. Interesting word, variability, in sample means, okay? And again, you can see that. You can see it's a greater variability. And later on in statistics, you'll see a term called variance, okay? And also we talked about something called standard deviation last lesson, okay? So these are other things that you might want to put in your memory bank somewhere. Just stow them away, okay? But anyway, yeah, just basically here, the first one shows a greater variability in the sample means. As you can see, goes all the way from 34 to 78, whereas here we have, 41 to 65. Okay, so there's greater variance or variability. Okay, so the second one, which dot plot do you feel more confident? That's up to you, I guess. Very personal. I would have to say the second dot plot for me, because what I have now here is I feel a little more confident because they're more tightly clustered, okay? You can see there, I'm getting some clustering here and here, so I'm really starting to see that these are means of 20 different samples of 15, okay? And I also feel a lot more confident with having more data points, okay? So I have more clusters, I have a more narrow range, okay, and I have more data points, okay, which is really, really important for me, okay? All right, and again, that was up to you, but hopefully you're starting to see how something like that second dot plot would be a little bit more, you'd be a little more confident in it. So in general, do you want sampling variability to be large or small? Well, of course, that's the point of this whole thing, and of course you want it to be small, okay? You want a smaller variability so you can feel safer coming to any sort of quote-unquote conclusion, okay? Because what you're doing is you know that somewhere in the middle, okay, of all this mess of dots, okay, there is your mean, okay, your sample mean, somewhere in here. With this second dot plot, with the lesser variability, you can see any single answer, okay, any single mean, okay, is not as far away from that mean, from that middle, than any other point. Okay, you can see again this whole clustering here in the middle. Let me just make it a little right here. So you have this. Any one point is not as far away from the mean, the true mean, as is the case here. Okay, so you can see what a wide variability there is there. So again, you want it to be small. It increases your confidence in your conclusion. Okay, well, as you can see here, in the previous lesson, we found sample means of using 15. Okay, I'm sorry, using 5. Today we're going to be, or this lesson, we're going to select a sample size of 15 from that same population, and then we will calculate the sample mean. So we're going to do exactly what we did last time, but we're just going to up the sample size, okay? Up the sample size, each sample size to 15. Of course, we are not going to do any of this because this is about that silly random number thing with the eraser and all that, okay? But what we will do is I'm going to go ahead and use my random number generator. If you want to go ahead and jump on yourself, hopefully you bookmark that thing. You can do the same, but I'm going to go ahead now and generate 15 random numbers between 1 and 800. I will write those down here, and then we'll go ahead and do what we did yesterday and find those values, calculate our mean, and then go from there. Well, there's one thing this is, it's time consuming, so get used to it for the future. So anyway, I went to my Rossmann Chance applet and generated my 15 random numbers. Okay, and here they were. They came out to be this. Okay, you don't need to worry about this because I went ahead and generated, figured all those out. And here are my 15 times, okay, 15 times that I came up with on this chart of 800, and you can see them here starting from 63 and on the way down. So what I'm going to do now, I haven't done this yet, but if you want to just pause here, you can go ahead and find the mean and see if you are calculating your mean correctly. Okay, I'm going to add all these up, of course, and divide by 15. So I'm going to do that right now. Okay, so I went ahead and did that, added all these values up, and came to a mean of 58.3 because it asked me to round to the nearest tenth, okay? Be sure to show your work, yeah, okay, I can't really hold you to that, of course, but here's my work, okay, all of my numbers, and then into my calculator, and that came up. So there we go, 58.3. So now the whole idea is you will now use the sample means from exercise 3 for the entire class. Again, an impossibility. Okay, we can't do that. We don't have all of you here to make our dot plot. And again, writing the sample means down here for everyone would go in number 4. Use all of those means to make a dot plot. Okay, and we could have done it here. I could plot mine right now. So 58. 55, 56, 58. So mine is going to be about right here. Okay, and again, if they were close, we would just have them stacked on top of each other. So let's go ahead. Maybe what I'll do is right now, let me go ahead and calculate some more samples, and then come on back and plot out, I'll just say 14 of those, because that's what we are. We're a class of 14. I'm just going to I'll make them up, or not make them up, but I'll go ahead and generate those. And again, remember, this would be n equals, if you know, or if you remember what that n would equal 15, because we are using 15 data points per sample, okay? And that, right here, that one dot right there is just my one sample, okay? So one sample of 15, okay, and that's what that dot is right there, okay, one sample mean, but it'll be very specific, of 15, okay. That sample mean was generated from 15 different points of data. Well, rather than do that, I think what I will do is leave that up to you. If you would like to go ahead and create several samples of 15 data points using the random number generator. The truth is there are some points to make in this lesson. This activity is just a lot more fun and revealing as a class. Kind of silly for me to continue to do it, but let's just talk about some of these things. That's pretty much what we'll do here. Let's just go ahead and just talk our way through the rest of this without actually collecting any more data unless you would want to, because I think it would be quite revealing. I would appreciate it if you did. I can't make you do it, but if you did get your random number generator going on the internet with that Rossmann chance or any other random number generator, that would be super. And go ahead and make a bunch. If you made another like 14, 15, 20 different samples, and just to see where these dots would fall, it'd be very, very, very interested to find that out. And you can use mine. There's mine right there. Remember, mine was 58.3, so you can always use that one. Okay. So again, in the previous lesson, just talk about all these. You drew a dot plot with the sample size of 5, if you remember. Okay. How does the dot plot above, with the 15, n equal 15, again, sample size being 15, how does it look compared to the sample size of 5? And which do you think has the greater sampling variability? Okay, so the greater sampling variability, okay, which is really important, is going to, it won't always, okay, you can't guarantee anything, but the greater variability is going to be with the smaller sample size. Okay, so when you have a smaller sample size is going to equal greater variability. Okay, and the greater the variability, the less reliable our data is, or our statistics are. Okay, so when you have this smaller sample size, you're only taking 5 of those 800 data points, and you're using those to create a mean. Whereas when you have 15, you're adding up 15. So there's a greater chance again of taking numbers. If you take a very small number, for example, you pick a very small number from that sample. If you have a larger sample size, like 15, there's a greater chance you're going to get a higher number that'll kind of even off that smaller number. And that's what it's all about. And again, I've said this 100 times, and I'll continue to say it. Statistics is just about being as perfectly imperfect as you can be, okay? Because that's what it's all about. All right, so and again, this exercise illustrates, again, we really haven't done the whole exercise, sorry about that, illustrates that notion that greater the sample size, the smaller the sampling variability, okay? All right, and that's just the opposite, of course, what we said here. Smaller sample, because the inverse, is greater variability. And then we have greater sample, the smaller variability. Okay, let's just keep plugging on through here. Now, just to know, and they've said this before, but remember that in practice, you only take one sample, okay? Suppose a statistician plans to take a random sample of size 15 from the population of time spent at the gym, and will use the sample means as an estimate of the population mean. Okay, now the population in this case is 18. Sorry, not 18, 800. And that in statistic symbols would be an uppercase N. Okay, so the N, this is the population, is 800 because those are 800 times. And then we have the smaller n. In this case, the n equals this lowercase n equals 15. Okay, so based on the dot plot of sample means, well, we can't actually do that. How far? Well, I guess we'd have to use that to actually see. But do you think this? Do you think taking a sample of 15 and extrapolating or coming to conclusions about a population of 800 is a reliable thing to do? That's something to ponder. And would you just go ahead and ponder that? Okay, so let's go ahead and talk a little bit about this here, number 7. So based on the dot plot, sample means that your class collected. I'm going to show you something I got from the teacher guide. Approximately how far can statisticians expect the sample mean to be from the population mean? Okay, so they're actually telling you right here the actual population mean is 53.9. So somebody actually did add up all 800 of those times and divide by 800, okay, and I got 53.9. This is the actual population mean, which is interesting because that's not too far from my 58.3, not too far. But anyway, if you take a look here, okay, this was what I was talking about before, this idea of variance, okay? This idea of variance, or remember I told you about standard deviation, and we're trying to find out how far each value, the average value or the mean value, is away from the actual mean, okay? So the actual mean here, we're using the actual mean, okay, equals 54. We're going to round it to 54, okay? So now they took a sample here of various means. Now these means were taken from 20 samples, and they were samples of 15, size 15. So in this case, the n was equal to 15, such each sample had 15 data points in it. Okay, so here are the sample means that were achieved in those 20 sampling activities, as you can see right here. Okay, now over here to the right of them here, these are the distance from the population mean. So the 13 here, for example, is, you know, the distance between 54 and 41. Okay, is 13. All right, and again, it doesn't matter if it's negative or positive. We're just looking at distance. So in this case, we're looking at an absolute value. Okay, so we're looking at distance away from the mean. And as you can see, if you do, the way to find the average mean, or the mean of the means, okay, the mean of the means, the way you would find that out, you would actually go ahead and, well, not the mean of the means, but the mean of the differences, or the variances. Okay, you would take all of these, and add all those up, so you have the sum of the means, and the sum of those means equals 137. Okay. All right. And then you can divide that, of course, by the number of samples we had, and that was 20, and that equals 6.85 minutes. So the mean difference, or what you will one day come to know as the standard deviation, was 6.85 minutes. Okay, so you could, when answering this question here, it says approximately how far can the statistician expect the sample mean to be from the population mean? Okay, if we took this data, we could see that he or she could expect to be about 6.85 minutes, or about 7 minutes from the sample mean. Okay, so if we looked at a couple of these, actually, if we looked at well, the person that got 41, or the people that got 41 for their mean, those samples. Okay, they could predict they're about, if they said they're about 7 off, that means they would say, oh, then it must be about 48. Okay, which wouldn't be correct, okay, because the actual mean is 54, but at least we are accounting for averages. And again, this whole perfect imperfection, okay? So that answer to that would be the answer to that question number 7. Now, I don't want to go ahead and do it, but how do you suppose your answer in exercise 7 compares to the equivalent mean of the distances for a sample size of 5? Okay, so you're thinking here, this is all sample size, or here, so sample size of 15, and you have this, the average difference being 6.85 minutes, okay, was the average or the mean difference, okay? Now, do you suppose if you had this sample size now of 5, would that mean difference or standard deviation, would that be More or less, do you suppose? This is just a common sense question, actually. And of course, it would be more. Okay, it would be greater. Okay, it would be it would be greater. Okay, because you're going to have because of a greater variability. Okay, of a greater variability. Because if we looked at those, actually, if we go back and look at those dot plots, okay, early on. Here. Yes, here. So again, this big mess I've made here, I'm going to go ahead and just erase all that. Okay, and if you look at these dot plots, okay, again, the top one is n is equal to 5. That means sample size was 5, 20 samples of 5, and this was 20 samples of 15. And you can see from that, look at that wide variation, okay, wide variation of scores. So there's going to be a greater average distance from the mean, the actual mean, in this one than there will be in this one, because you can see that, that spread or that variety or variable nature is much less. Okay, it's much less. So again, some things to think about, larger sample, less variability, less mean difference from the actual mean. All right, smaller sample, greater variability, and a greater mean distance from the actual mean. Okay, I know it's lots of means thrown around there. Okay, so and we're just going to do a suppose here. Here we go again, another question. Suppose everyone in your class selected a random sample of 25 from the population times spent at the gym. Okay, so now we've gone from 5 initially up to 15. What do we notice? We notice that our variability is getting less as we go up. So what do you think the dot plot would look like of your class's sample mean? What would that look like? Make a sketch if you'd like. Okay, and hopefully on that sketch, and again we can compare here. Let's look at these again. If we look at these two, you can see if we're going to have now an n equal to 25, what we will probably see is a dot plot. What we are going to see, if we have an n equal to 25 or sample size equal to 25, we're going to see a greater cluster to the middle. Okay, this is what this is what we should we should see. Okay, and again, should. Okay, in a perfect world, we should, because as we get a greater sample size, our variability should shrink. Okay, again, that's not always going to be the case, but that should be the case. Okay, so to answer this question, it might look something like this. We know the actual mean is 54, so you're probably going to get a greater cluster around this middle part, maybe 1 or 2 here, but your variability is going to shrink. Okay. So suppose a statistician plans to estimate the population using a mean sample size of 25. According to your sketch, approximately how far would the statistician expect to be from the mean? Well, we don't have to guess something like that. What we do know is that at n equals 15, at a sample size of 15, we had a mean distance away from the mean at 6.85 minutes. And all I can tell you, and hopefully you would guess this as well, at n equals 25, what we should expect to see is something less than that. Okay, less than 6.85 minutes. Okay, and that's all we could assume. Okay, and so finally here, number 11, suppose you have a choice of using a sample size of 5, 15, or 25. Which of these three makes the sampling variability of the sample mean the smallest? Okay, which of these makes the sampling variability of the sample mean, the smallest, and of course, we would know, and you should guess that it would be 25, okay? Why would you choose a sample size that makes the sampling variability of the sample mean as small as possible? Why would you want to do that? Why do you want to keep that sampling variability small? Well, you want accuracy, okay? You want greater and greater accuracy. You want to be able to feel sure that you are less and less far away from the actual mean. You want to be as close to the actual mean as possible. Okay? Because the truth is we have, let's say we have, for example, we have 360 million people in the United States. Okay? We are trying to find the average height of those 360, or maybe we should start with, let's say, adults. Let's say people, citizens over 18, okay? And probably bring us down to what? I don't know, 240 million, okay? 240 million people. Well, of course, we can't go out and measure all 240 million people, so we would need to get a sample of people. And again, this is more complicated than it sounds, but the point is, the more you get, the more samples, the more people you get to measure their height, the closer and closer you're going to come to the actual mean. Because the truth is, you could take the heights of all 240 million people and divide what you get by 240 million, and you'll get an actual mean. So there really is an actual average height of an American human being, okay? But of course you can't do that. But the larger you get, the larger the sample, the closer and closer you get to that actual mean any time that you pick a sample, okay? And yeah, that's what it's all about. All right, so lesson summary. Suppose that you plan to take a random sample from a population. You will use the value of the sample statistic to estimate the value of a population characteristic. And if you remember that a long time ago, that difference between a population's characteristic and a sample statistic. Again, the sample statistic is, is gleaned from the sample, okay? Gleaned from sample. It's something we could say about that sample particularly, okay? Now the population characteristic, okay, of course, is actually applied to a larger population, applied to entire population, okay? So if we want to say, for example, in this activity we just did, that the what we came up with, my sample was 58.1 minutes average time at the gym, okay? That's my sample statistic, all right? And I can only estimate that population characteristic from that. So if I say that, it needs to be, I need to be as certain as possible, okay? And to be as certain as possible, I want, you want, we want the sampling variability of the sample statistic to be small, so the sample statistic is likely to be close to the value of the population statistic, characteristic, close. We are trying to get as close as we can, okay? And we will never, well, I won't say never say never, okay? If I can teach you one thing, children, never say never. Anyway, the chance is not great that we would actually be exact, but we can get closer. And the way we do that in statistics is to increase the sample size, okay? Increase sample size, shrink the variability of the sample mean, okay? And that's what this lesson was all about. Have fun with the with your pages. And again, any help you need, just give me a call.